We shouldn't just get some media or mainstream advertisement. This is something that we really need to check. Like, we just hear, oh, this model is just released, it's the best one, let's just go and use it. No. We have to, really focus on our own use case, our own concept, the total cost. We also need to remember, as I said, that the biggest model is not always the best model. In this talk, we will talk about all of the pros and cons and how you should go through the selection process of such a model. And what is the difference between fine-tuning and RAG? Nice to meet everyone. Thank you for joining. My name is Nahid and I'm happy to be presenting today. I'm currently with Microsoft and I have been with several companies in my past. Graduate of Virginia Tech, teaching at Berkeley. And today we are going to cover basically how to select an LLM. How are we going to choose an LLM? How are we going to fine tune them? And what is the difference between fine-tuning and RAG? I do want to start with saying that we do have different types of model. We have open source models and closed source models. Primarily, we have, in case of open source, we can, for example, find an example of GPT open source like GPT OSS or LLM and or Mistral. Or you're probably familiar with closed source one, or from OpenAI, got GPT-5, or from Anthropic Claude. All of these are excellent models that have a lot of capabilities, but there are pros and cons with each, sort of the option that you may want to pick. In this talk, we will talk about all of the pros and cons and how you should go through the selection process of such a model.
If you are liking this video, then you love what I have to say next. You can spend months learning agentic AI or cut that time into half with a structured program by Interview Kickstart, where you actually build and ship 2 AI agents into production with a mentor from Faang guiding you through every step. It's called Agentic AI Career Boost Program. And if you think it's just another generic course, spoiler alert, it's not. It's customizable depending on your domain. Engineers, you have a Python-based AI engineering path. If you're a PM or a manager, you take no-code, low-code use case path. And both paths could be paired with Faang interview prep for AI-driven roles. But the best way to learn more about this program is through the free webinar. Here you can get all the details about the program, ask your questions, and see if it's the right fit for you. And if it is, you'll be joining a company of 25,000 professionals who have already leveled up through Interview Kickstart. Many now at Faang, Anthropic, OpenAI, already crossing 300K plus. And here is what some of them say. I'll put the link to the free webinar in the description, as well as pin it in the comments so you don't miss it. See you all there.
With open source models, what really makes a model open source is that you will have access and you will have an understanding of what the weights are in the model, what data was used to train the model, and that's what really makes it open source. With the closed source model, they really don't share much information other than, giving you an API endpoint and giving you documentation on how to use it. And as a consumer, you really don't know what the weights are, and you have no way to change the weights for these models, and you really don't know what data they use to train the model. And so this is the main difference here. So in case of open source, you will have full control, it can be customizable. And when it comes to proprietary model, they are heavily funded, so they do have a lot of resources, a lot of data at their disposal. And they come up with new features. You will see memory activated, reasoning activated. So one of the benefits you have if you go with a proprietary model is that you will get access to all those premium features. And we can have hosting a standalone model or host it on a local version. It can be on-prem or in the cloud, and we can manage the open source models ourselves or get an API access point. So from a cost perspective, open source models, you'll see that based on, the scale, there is, we can plot our usage, we can have a graph model, and depending on the company and the use case, we can hit a certain amount of usage. With the closed source model, they can get expensive over time as you start consuming more tokens, and we look at more, some of the decisions that you have to make in terms of cost selection. But once we have like larger volumes, the proprietary models can get really expensive. Whereas, in open source, we have a fixed cost, regardless of whether you have, 5 million requests a day or 1 million requests a day, it's probably going to cost you almost the same, other than, infrastructure cost. So that is something, you have to just keep in mind when you want to make a choice. When it comes to size, you can see that we have different sizes of models. We have smaller models that can have like 1 to 7 billion parameters, and then medium size up to really large size that nowadays are going to trillions of even parameters, I guess. So you would want to make the selection based on the use case, and you shouldn't just think that the biggest model, the largest size model is going to be, the best choice for you. And it may not even suit your use case in this case. And so when we want to select an LLM, there are four main key factors that will help us make a selection. And it's, really across performance, technical side, business side, and of course, security side of stuff. And we can dig into each of these one by one. So from a performance standpoint, what you really, want is how well does your model perform. In terms of performance, you can think of what is the context length in terms of how much information can the model remember while you're working with it. And it can vary quite a bit. So for example, if you look at Gemini, or the Pro Series model, they can actually support up to 2 million tokens. So very large context window. And then there are some smaller models that can be anywhere around like 128K or up to maybe 400K context window. So you do want to understand what the context length is based on your use case. You also want to look at how reliable and accurate your output, the output of your model is, depending on your use case, whether you need reasoning capabilities or not. You need to evaluate what performance expectations you have. Like a PhD level mathematics versus, an assistant bot are very different in terms of, the capabilities. Do we really need, some abilities or not in terms of, evaluating how well the model is performing? You can look at, there are like many resources, there are benchmarking resources that can help and evaluate different LLMs. Sometimes we want image extraction, sometimes we want OCR, sometimes we want reasoning. So that's, something that you have to evaluate. And there are, lists of different LLMs and leaderboards that you can check for performance evaluations. But also you need to understand that you need to check for your own use case, and you test based on your own benchmark and come up with a final assessment for your model. From a technical standpoint, you definitely want to look at the latency, and it is very critical if you have, real-time application, or for example, if you are building a chatbot, maybe it's a live chatbot, and maybe customer service sort of chatbot. You have live customers asking questions and they want to maybe look up another question. So speed and response time really matters in these critical use cases. And or for example, if you are doing some sort of, batch processing where you're doing some language translation, you have documents that you need to translate from English to another language. You don't have to, this doesn't have to be really real time, and you could just run these in batch mode. So there's a difference. So especially like with closed source LLMs, yeah, you can have, batch tokens, get batch tokens, and they are less expensive compared to real time on-demand responses. So that's something you can consider. You would also want to look at the scalability. All the different providers, whether you are directly going to one of the providers, Grok or Google or anywhere else, they have restrictions based on like the transactions per second that you will need for your use case and how many requests you will have. or whether concurrent requests can be submitted to their API or not. So you would want to look at that as well. That is actually going to impact really your experience of your customers. On top of that, some of the infrastructure requirements really matter. This is if you're going to, whether you're going to host it yourself or are you going to using an API, then maybe it doesn't really matter. You don't need any compute. But if you are running the model, if you are using it for inference, that is the case. But if you own the infrastructure, you want to make sure that you have the right hardware, GPU to be able to run the model on your infrastructure. Then you also want to look at what are your, deploying and hosting options are. Do you want to deploy this into the cloud or on-prem? Especially, some of the larger organizations still have, some on-prem presence, unless, you are a startup or smaller organization. Finally, most of, the major mainstream providers, they have APIs, they have SDKs, very compatible. They even provide with different languages, like API keys or API capabilities for you. And you just have to install their SDK libraries and just with a language of your choice, and you can move on. But with the smaller, models that don't have like a lot of support, what is going to be the option? What sort of support are you going to get? Do you even have like capabilities to implement those SDKs yourself or not? Then we move to business standpoint, which we talked a little bit earlier. You do want to look at, token pricing, and they are very different. There are variations in both input tokens and even output tokens. Usually output tokens are more expensive. You would want to make sure that you do your due diligence when it comes to pricing. And if you are going to be hosting your model on your own infrastructure, what are the costs for that? Like, do you have development and integration costs? You want to look at, the big picture. You want to also look at the cost of ownership. It includes the hardware, the software, the development, and even, training part. And so big picture, or from an organization standpoint, if you have a business leader, making such decision, then you are going to be making it in terms of picking and making some of the choices for LLMs. And I think, a lot of us have seen many reports that companies made big investments in terms of LLM and they are not seeing the value. And this could be one of the reasons, like something that we want to make sure to look at the vendor, the ecosystem, what type of support you're going to get, especially if it is an open source model. Like what if you are, the model provider gets acquired, what sort of support service they have, what sort of contract, what sort of documentation they have. And so that's the space that is growing really quickly, and you would want to be predicting what could go wrong in this case. Finally, security, which is a topic that is very close to my background, is something that you'd have to, really read the privacy guidelines and the security guidelines for each model and the model provider. This is where you need to do, your homework. Generally, with a lot of the paid models, they're actually going to be like closed source or proprietary models. You are usually paying to use the API. Or does the company has a custom agreement or like an enterprise agreement? They generally, are not using your data to train your model, but that is something you would want to make sure to check, because the privacy of your customers are really important. How the data is being processed, where is the data being really used, and is the model that, we are accessing, is that dedicated to our organization or not? Is it shared with others? What sort of, data and access controls are implemented in this case? And you'd want to figure out how it's actually working when it comes to the provider and where the model is being hosted. There are a lot of industries that are regulated, whether you are in, for example, healthcare or financial banking. They have different regulations. There is like FAIRPA, HIPAA, SOX that we need to stick to in industry regulations. From a compliance perspective or risk perspective, we need to have auditing trails in place. And this is something that you would definitely want to, test with your own data. so to get better evaluation. And typically these models have guardrails to prevent some sort of toxicity or harm, or security checks to detect prompt injection, or to detect document prompt injection. But you do have to do your own test or get some certification or verification that these security guidelines are aligned with your business use case. Sometimes I have seen models using a specific LLM in the background and implementing a lot of responsible AI and security privacy guardrails around that LLM in their own environment. So in summary, if you are looking to select the model, there are things that we need to really care about. We shouldn't just get some media or mainstream advertisement. This is something that we really need to check. Like, we just hear, oh, this model is just released, it's the best one, let's just go and use it. No, we have to really focus on the our own use case, our own concept, the total cost. And this could really go bad if we don't do our due diligence in these cases. We also need to remember, as I said, that the biggest model is not always the best model. So we'll talk a little bit about that. Depending on your technology in your roadmap, you have to decide what you need. Usually, in these cases, we need to kind of go backward. First, look at the business requirements. If we are technologists, of course, we want to choose the best model with the best capabilities. But do we really need that? What is the cost of that? Then what solution is a best fit for us is what matters here. Now let's move to the next phase. Let's talk about a framework so that can help you actually choose the right LLM for your use case. And there are, as I said, another 4 steps that we go through this, that the backward process that I told you about includes 4 steps. We have the requirements gathering, and then this is where we recommend most of the customers to spend their time on the requirement gathering. Once they have really buttoned down a set of requirements, that's where we actually want to move to the evaluation phase, and we actually test it and we go through the test, and finally we start the deployment. So starting with business requirements, you really want to figure out what the use cases or what the business problems is that this LLM is going to solve for you. What are the specific tasks and this is LLM going to perform? Is it going to be used for summarizing text? Is it going to be used for, customer service chatbot? Is it going to be used to generate code? So you really want to figure out what exactly are these use cases, and you want to define success criteria for each of these use cases. So what does really good look like for you? Without having the right success metrics, it's going to be very hard to measure and evaluate what is the next phase of the framework, right? We have to be able to evaluate it. We also want to understand what is the user experience going to look like, especially if it's going to be a real-time model where someone is going to be interacting with it in real time. What is the best response time look like for you? How about the UI? What does the inference look like? Does it need to integrate with other systems in your organization? In most cases, these LLMs generally have to work with other systems in the organization. So you really want to understand what does that integration look like. Again, from a volume perspective, you want to know what sort of load you're going to expect this model to generate, because it's going to be translated to requests and transactions per second, transactions per minute. So you want to factor in also your plan for growth. In real world, we do have constraints. For example, money is one of them. The number one constraint is kind of like budgeting. And so, what budget constraints your company has, what is the timeline for your business stakeholders there. And the answer usually is like very difficult to get, but this is the requirement that you need to make sure that you gather. You also need to understand the security and compliance requirements. Is this a regulated industry or not, and what those regulations are. And what are the technical requirements in terms of, again, the infrastructure, being able to understand the skills and capabilities of your team. If you need to build some sort of, training or enablement program for your employees. And then as a result of that, we have to create such matrix. And these are just samples, but you can adjust based on your own use case. You can give it different weights as you like, but it should, eventually, or at a minimum, conclude these at least five categories of performance, cost, latency, security, and support, and then assign it different weights. Then there is, like, if we have model A, model B, model C, we can actually look into each of these and make a data driven decision. Then we move to the testing and validation part of the process. This is where we actually use real examples from your organization. You would want to make sure, to test some of the edge cases. And it's very easy, to test sort of, most routine common cases. But it's important to, think about a few edge cases. So this is where you are making, able to handle any sort of errors or unexpected behaviors and, like, boundary conditions. And you definitely want to involve actual users. And many organizations make this mistake that they just like make decisions by the IT team or the whole company's data as testing data, which is a wrong thing to do. You have to involve your customers, you have to dog food your process, you have to get feedback from them. It should be an iterative process, and you need to build on top of what you already have. And in terms of, success metrics, you can have quantitative and qualitative. You can look at, the response time, cost, accuracy, and you would basically measure those and document those. And then you will have quantitative, like how easy is it to integrate, what is the user satisfaction. Those are some things you would want to make sure, as part of your evaluation, you have considered. So you pick a model and you want to make a decision. This is where basically, you use your evaluation matrix and make a data driven decision. And so then we will have, the final deployment process, and we have to, to see how our organization can, now that we have made a decision, what is our deployment strategy, and how do we, fine tune the model? How are we going to now change the model if we want to? After successful deployment, our organization needs to see also, like, what is our support and operation process. Anyone in our team needs to learn the new skills to integrate or use this model in their daily work. What are the integration requirements, any security or governance? At the deployment time, we should think about logging and auditing and monitoring all of those logs. So these are the processes for going through selecting a model. Imagine now you have selected a model and you deployed it, all look good. And now you want to, see how to fine tune the model. So we will talk about a little bit about fine tuning and how does it, compare and contrast with retrieval augmented generation. So when it comes to, taking a model and injecting it with domain specific model knowledge, these are really, fine tuning and RAG are two broad approaches that we know of. You can either fine tune, which means that you have some specialized data you use to train your model, versus the retrieval augmented generation or RAG. You're basically having the model do a lookup, or actually you have, maybe some code that sits in front of your model and it does a lookup from an external source. And then it will be able to retrieve some information which it can then use to inject and add more context to your model. So the response is more grounded. So we'll take a look at, what the two approaches are. When you look at fine tuning is a way to adapt an existing LLM without retraining it from scratch. So when you look at the purpose of fine tuning, it's really to add domain specific knowledge and domain specific data to the model. For example, sometimes the knowledge base have a lot of, specialized terminology or maybe jargons. This could even be like company jargon or industry level jargon, which the model may not know. So what the context or what some of those words really mean. And a regular, sounding word might mean something different in a specific industry. We can also, fine tune to adapt a style or even personality in terms of how the model acts, in terms of culture, how it behaves, or even its language or its style. So it's matching your specific organization. You can optimize it for, some very specialized task. We will take a look at, a demo in a little bit. So for a specific industry, healthcare industry. So you can really think of, fine tuning a model and turning it from generalist, because these are large language models that are trained out of, large amounts of data, to a specialist. So that is the purpose of fine tuning. So we talked about, fine tuning, really embedding knowledge directly into the model. But when we look at RAG, it's basically a mechanism where LLM basically gets external documents during the inference time. So when a question is asked or when request comes into the picture, there's usually a piece of code or in the application that is sitting in front of it. And this code is actually performing that RAG or information lookup, knowledge lookup for you. And it could be, doing a search or query in the internal system or any other, connected systems. And then it's going to use the response and basically augments the context for the model. And in reality, when we want to, perform the accuracy of our model, or when we say, oh, do we need to use fine tuning or do we need to use RAG? Usually we go with the best of the both worlds. We can combine both of the solutions and it will give you better resilience and a fresh and an accurate data as well. There are some myths, and I actually do see some of them in the questions. And then when it comes to fine tuning, for example, some people say fine tuning doesn't new information. It actually does fine tuning because it does add new information, because what it really does is it goes through the different parameters and it basically looks at the neural network and then it only modifies certain parameters within that neural network. So it does add new knowledge as part of changing that neural network. You may always hear that like, oh, RAG is always better. It's not necessarily true. It depends on the use case, and we'll actually look at some techniques. May hear fine tuning is expensive. Again, there are methods of fine tuning that are cheaper and they don't need a lot of compute, and we can actually do them on our normal computers. Some of these methods named LoRa and QLoRa, which is quantized LoRa, and they are efficient and cheap when it comes to fine tuning a large language model by adding small trainable adapters. So typically, if you were to fine tune a model, that's very expensive process. It takes a lot of data and lots of compute. But when you use the LoRa method, what it does is that it doesn't go through every parameter. So if your model has billions of parameters, it actually just goes through a few of the layers of your neural network, and then it only trains a few of the adaptive layers in your neural network. So it is more efficient. There is only a few parameters that being updated. And when you look at, the QLoRa or quantized LoRa, it's basically LoRa where we reduce the precision, where you might lose, some amount of information because you're going down from 16 bits to 4 bits. You will lose some information and precision, but then you have the ability to run the fine-tuning process on some commodity hardware, and you are not going to need very large, huge GPU hardware. And I'm going to go through the demo to show you an example of a fine-tuning. I already did run the model. Let me make sure you're seeing the screen. Yeah, so I have it in Colab. You can have it in Jupyter Notebook. You can actually run on your personal hardware. And we are going to, to walk through of different cells. First, we are installing, we are going to install Torch and we are going to install Transformers. Transformers is an open source library and it is developed by Hugging Face. So you can think of Hugging Face as the GitHub for machine learning, and then we are going to use Transformers reinforcement learning library and then the Hugging Face. And in my case, I already installed it. It shouldn't take a lot of time and it should just simply say install. Let me just try to keep running this and my collab getting connected. I just want to show you the Hugging Face. So you can actually open a free account with Hugging Face and you can get an API key from Hugging Face. It is free. So we can use any of the Hugging Face models that we want to. And they are open source models that you can use, and you can even download some of those models and use them locally, and you can you can also have inference of the previous model. So you can see, you can go to your Hugging Face token page. I did have my token already prepared. Hopefully it is not expired, but we'll see. Right, you can, yeah, this is how you'll get connected to Hugging Face. And it's a free account, and then you can define what sort of hardware you have. Maybe you have a MacBook, maybe you have NVIDIA GPUs, or maybe you have a CUDA driver, something like this, depending on what you have enabled. Even on the Colab, as far as I know, you can have some cheap GPUs, so you don't really need very sophisticated hardware for this case. Now this is the important part that we are looking forward to. So I'm going to actually run this because it may take some time. We are going to import a couple of libraries. We are importing the tokenizer library. Then we are importing some sort of model. It can be any casual LLM. I was trying before the session with different models, Quen or Instruct models, or you can actually also get an AMA Instruct model. And the thing with Instruct models is that all of the Instruct models are basically good for chatting and chatbots, and you can ask the question and get an answer out of the result of it. And they are pre-trained as assistant models. You could use even large AMA models. All of these are free, but for us to be fast, we are just using a simple small model, and we are just trying to interact with it with the roles defined. For example, I'll say, oh, I am a 35-year-old female with fever and rash, and please summarize. Depending on the on the model that you are using, you can see different sort of outputs. And this is kind of like taking a little bit longer than usual, but the output that we will see are here. For example, it is kind of like hallucinating. Why is it summarizing like this? You can see that it is just talking about similar symptoms last weeks. At some point I had responses that talked about COVID, and basically just giving us answers that are not appropriate. And if you use the closed source models, most of them will tell you, since they're closed source, they will say, oh, I am not even able to talk to you because you are like, this is health related information, I'm not allowed to talk to you. Now we want to fine tune it with some information using a JSON file. You can simply upload any sort of extra information that you have. Here I have a healthcare data in the JSON format, and it's just the format is that it has consultation, and it has a summary field, and it will talk about the blood pressure, heart rate, etc. So it does have a specific format. So if you remember when I was talking about building culture or building persona, this is a use case where fine tuning is going to be very helpful for you. This JSON file that I have is very small. I'm not even going to run the cell because it will take about 20 minutes on CPU to fine tune. I just want to show you the code. And then, okay, after we uploaded, the healthcare data as our training data set, now we are going to build, the configuration file. We create output directory. The beautiful thing about it is that you can actually upload your output directory and push it to Hugging Face interface, and you don't need to retrain and fine tune all the time. You can just use, or you can actually download it locally in your local Jupyter notebook. We are running it for 3 epochs because I have limited resources. I just had CPU, and you can see that the training data that we are giving it, and you can give it any hyperparameters that you want depending on the resources that you have. But for it to be pretty quick, I decided to just use the CPU and then a small learning rate in this case, because I don't want it to have huge jumps. And right, yeah. And then we will go to train the model or fine tune the model. This is the part that I said is taking about 15 to 20 minutes to train. It takes long to run, but what it is doing is that we are feeding the config as well as the data set, and we are saying use the tokenizer and the reinforcement learning library that we talked about. And you can see here the training took a decent amount of time. Oh, actually about 39 minutes when I ran it previously. And you can see that the loss is going from, 0.9 and keeps improving and getting better and better with time. I do recommend you to look into the Hugging Face hub. You can push your model to the Hugging Face hub and you can actually use it later. We go through the second step again, but this time we are loading the model from our directory that we push to with the same calling, similar stuff. This time I passed in, similar query, for example, 50-year-old female with fever and rash, and you can see with just 3 epochs and minimum training and 100 rows in a JSON file, you can see the summary is looking very similar to what we had in the JSON file for fine tuning. So now you can realize the power of fine tuning in building personas, in building a specific domain specific responses in this case. I will stop for questions. Rohan?
No, there was an accidental click. Sorry, I was reading somebody else's hand, so I clicked mine on. Sorry.
Okay, yeah, no worries. I will try. I am seeing the questions. We do have another demo and we are talking about agents. So I definitely want to get to those parts as well. I will answer the questions at the end of the session for sure. So this was our first demo. Highly recommend you to look at the Hugging Face. I already know some of you may be asking, how am I going to compare, different models? Actually, Hugging Face has leaderboard, it has comparison of different models, and it has a library of models you can pull from. It's a great community. You can ask questions, several data sets, models out there, and it is free. So, why not? All right, so going back to my slideshow and just summarizing what we discussed is fine tuning versus RAG. We can combine them. There is no requirement, to just have one of these models, and think about or research about, cheaper ways of fine tuning. It doesn't have to be a very extensive task. Moving to the exciting part, agents, they extend their capabilities by calling functions and APIs. I am trying to build a bridge between the end of today's session and tomorrow's session. So bear with me. Let's unpack now what really means when we say agents use tools. What is a tool? You can think of an LLM as a brain. It's capable of reasoning, language understanding, decision making, but by itself, it can't do anything in the real world. It can't fetch live data, it can't send an email or execute commands. Tools are how we give the brain hands and eyes. Each tool is like a mini function, a specific capability with clear rules. It takes an input, it performs an action, and returns a structured output. And you wouldn't believe in industry, what a huge need is for structured output. There are a lot of tasks for filing forms, but like going through review process, going through paperwork that can be eased by this structured output and identifying a lot of tasks. In practice, these tools are defined using something called function calling schemas. They are basically JSON blueprints that tell the LLM, hey, this tool expects a parameter named origin, one named destination, and I'll return a list of, flight options, something like this. If you want to, for example, build a travel assistant agent, it may have, web search API to look up flight prices, currency converter to estimate total costs, or a calendar integration. And, for example, we can think of many examples. Cybersecurity Copilot, it may call APIs that query, SIM service logs, trigger incident response playbooks, or look up, asset information, DevOps agent. So we notice, how each of these tools connect the LLM to a live and changing environment. Then that is how static text models can become dynamic systems and agentic systems. And tools basically extend the reasoning into an action for us. Now, once an agent has, access to the tools, the next big question is how does it know what to do first? Then that's where planning and control flow comes into the picture. And you can think of an agent like a junior analyst, and you can say, oh, hey, can you figure out why customer churn increased last quarter? And they can, for example, maybe they pull the data, they analyze metrics, they identify patterns, and then they summarize different findings. Agents do the same thing, except instead of we giving them a plan, the M creates it on the fly. And you can think of it, chain of thought reasoning. The agent thinks step by step, making explicit decisions, and then the planning, this planning behind the scene is managed through what we call a control flow, and defines like how one step leads to another next step. We can also have like some sequential flows, but also we can have branching or looping or parallel execution of the flows. In supply chain, for example, in supply chain scenarios, one branch checks inventory, another checks shipping costs, then they converge to calculate the total cost. There are different frameworks. For example, in a framework like LangGraph, it's implemented as a graph-based state machine, and you literally draw the nodes and the edges, and the agent walks that graph dynamically. It is structured enough for reproducibility, but flexible enough for the model's reasoning. And, with good planning and control flow, your agent becomes not just smart, but predictable, auditable, and recoverable. Now you can actually ask the main question: what is the difference between agentic AI and agentifying? That is memory. Memory plays an important role in agents. You can think about, agents' memory as, short-term memory or long-term memory. Shared memory can be like, oh, we are going to ask our teammates something, we all share that knowledge, or we are going to Google something, that is external knowledge, or RAG in this case. You can see how all the bits and pieces that we talk about are coming together to enable us to get a task done. Agents, mirror exactly that structure. Short-term memory, like chatbot, chat context, messages from each session. Long-term memory is persistent knowledge. It's stored outside the model, usually in vector database, which you recently learned. Shared memory, this is critical for multi-agent systems. For example, we have a planner, we have executor, we have quality reviewer. They need to share some data, and external can be RAG. Even, with memory, the model still needs to stay up to date with information, and that is where, RAG comes to the picture for us. And this combination makes the agent truly intelligent, not like it's starting from scratch every time. And that is the difference between agents. Now let's take a look at, the architecture. We call it a memory augmented RAG system. And traditional RAG pipelines only retrieve external knowledge from a document and they don't actually remember past interactions. Memory augmented RAG fixes that by combining retrieval with short term and long term memory. So the system can recall context from previous sessions, not just what's in the documents. And you can see the client query interface, that's the user entry point. Every question or command follows it from there. And then the first major component is the memory module. On the left, you can see the short-term memory and long-term memory and your vector store, which all the memories are encoded as embeddings and they have semantic set and all you learn here. Then we have, the retrieval module in the center that connects, to, for example, a document store like PDF, databases, SharePoint, whatever you want, and a search index. And this is where the system fetches relevant information from both documents and memory embeddings. And finally, there's a integration layer, and that is kind of like the fusion brain of the architecture. It takes the retrieved content and merges it with the current context. It has, two main sub functions. It has context fusion and the memory update. Context fusion combines the user query, memory recall, and all the retrieved documents into a unified context window for the model. And memory update, after the model generates a response, it writes important new facts or user interactions back to long-term memory. And then finally, you have the generation module. That is where the LLM produces the final answer. But you can, check the label that actually smartly says memory enhanced response generation. That is exactly what we mean. It means that the model's prompt now includes both retrieved documents and recalled memories. And yeah, another thing to talk about is checkpointing. So, for example, we've given the agent tools, planning capability, and memory. Now we need reliability, the ability to pause, resume, and recover. That is called stake and checkpointing. We can think about, as what the agent knows in the middle of the workflow, and that is part of, the state of the agent. Imagine like a system crashes midway, maybe after analyzing 10,000 record. Without checkpointing, everything is lost. With checkpointing, we can resume and go back to the last saved state that we had, and it provides us with traceability, enables backtracking, and you can roll back to previous state if the agent goes off track or fork from that point to explore alternative strategy. Checkpointing is for agents, like version control that we have in code. Checkpointing similar to that for agents. We have observability and evaluation. In traditional software engineering, we monitor latency, error rates, throughput. In AI systems, we monitor all of that plus a new dimension: correctness, safety, cost. Every agent should produce a trace, a complete record of what happened, which prompts were sent to the model, which tools were called, how long each step took, and what the final outcome was. And then there are, some metrics that you can check: response, accuracy, token usage, because you want to track your cost. And so these are all, parts of the observability. And it's like continuous quality assurance loop in this process. Moving a little bit quickly, we do need safety and guardrails as well. And the more capable your agent becomes, the more important it is to control what it can and it cannot do. Guardrails are very important. That is actually what I do on a daily basis. Input validation before the agent even acts. Check that incoming commands are safe and well formed. What if, they ask like delete all the records, and this should be flagged immediately. Scope restriction, define exactly what an agent is allowed to access. For example, a financial agent shouldn't be able to access HR data. Sandboxing, if your agent executes, code, do it inside a contained environment with no external network access or have automatic timeout. We need to have rate limiting, prevents infinite loops or excessive API calls. Agents can accidentally spam endpoints if reasoning goes wrong. We can also have like output validation. Inspect everything that the agent generates and make sure if it is sending an email, what are the recipients, if it's executing code, is it safe pattern or not. Some systems even use like a second model that call like and that model is responsible for reviewing the output. And finally, auditing is important for the sake of, compliance purposes. Right, so this is how AI guards agentic, like we should have guards on both sides, on the response side, on the input side as well. Quickly talking, a little bit, sorry, one sec, yep. Quickly talking about common architecture patterns. We have, actually first let's talk about multi-agent versus single agent. In single agent architectures, single agent handles everything. It's simpler, faster, and easier to debug. In multi-agent system, one agent plans, one agent executes other, critiques, and they need to communicate with each other. I did see a bunch of questions about MCP, Model Context Protocol, which is the way or a standard way for all of these models and LLMs to talk to each other. And that is where, MCP comes to the picture, as well as A to A protocol, which is for two agents, talking to each other specifically. There are, some common architectural patterns. The first one is REACT, which stands for Reason plus Act. This is where the model alternates between reasoning step and tool calls. It literally, thinks, and then acts based on the result. And there is self-act. The agent decomposes a big question into smaller ones and then tries to answer each sub-question separately. And then there is the tool former. It's models that are actually fine-tuned to automatically insert API calls when needed. It's very, actually less reasoning heavy, more automation oriented for repetitive tasks, things like that. And we have, we can design roles like planner, executor. For example, one agent decides what to do, another agent does it. Or we can have like supervisor, worker, a manager oversees several specialists, or delegation or handoff, agent pass subtasks to others or even humans when needed. And the analogy is that like a single agent is like a freelancer, a multi-agent is like a well-run team, planner, developer, reviewer, each bringing their own expertise. And the trade-off between these is complexity. In multi-agent, you need definitely an agent orchestrator, you need shared memory, you need coordination protocols, sometimes human oversight. But if it's done right, then it's really, scalable intelligence, a system that can reason and act. Now let's shift to the implementation. Actually, there are several frameworks, so you don't need to worry about all of these details. There are libraries that you can use. Frameworks makes all of these possible for us. And there's, that's where agent development frameworks help with tool chaining, error recovery, logging, caching, all of them, we can do it manually. And they can give you, the building blocks of what you are looking for. They can give you, code understanding. For example, imagine like an internal developer assistant that explains unfamiliar functions or find bugs or, auto documents codes. We can have summarization, for example, summarize customer feedback. We can have, chatbots, the usually most common entry point. We can have, Q&A with context and where the model references internal documents. We can have agents that are fully autonomous systems that can reason and act. We should have API integration, and there are frameworks like LangChain and LangGraph. They make it easy to integrate with APIs. And we can also have, tabular data queries, like, for example, show me Q3 revenue, product line, and forecast the next quarter, something like this. Quick introduction to the different frameworks. We have like LangChain, N8N, LangGraph, And just a quick overview, LangChain is the oldest and most popular. It's basically based on chaining different agents ecosystem. It is really good when you want fine-grained control, you want to define custom chains, you want to define prompt templates, memory buffers. You can have LangGraph, which is, the next generation. It's like a graph-based state machine. You can visualize and control your agents. It supports multi-agent orchestration out of the box. It supports checkpointing, and this is what we will demo. You can have human in the loop for your interaction. You can have autogen. It's a multi-agent first. It was developed actually by Microsoft Research, and it's scripted conversations between multiple agents. You can define agents like analyst, coder, reviewer, and if it's great for multi-role coordination type of work. You can have LLMA index. It's RAG kind of champion. It's also known as GPT index. If your task revolves around connecting LLM to structured or unstructured data sources like PDF or SQL or API, and that is going to be useful for you. It gives you, a connector, built-in connector with several data sources, easy index creation, querying pipelines, and it can also be integrated with LangChain and LangGraph. AI is newer. It's designed for teams of agents, and it's kind of like takes a lot of complexity away from you, and it has simple APIs that makes building all of these easier. And yeah, it needs minimal setup, so it's basically that's why the learning is actually quite easy. For you to choose the right framework, basically you have to define, your goal, your team, and your constraints. You need fine-grained control, observability, or custom logic, for example. Or then you'll, for example, go with LangGraph in this case. If you want to build data-heavy question answer, you will go with an AMA index. Depending on, what you need, this is how you should select your agent. For example, if you want multi-agent collaborate, you will go with AutoGen or Crew AI. So it all depends, on what sort of, subtasks you want, what sort of capability you are looking for. And finally, just a quick MCP note, it's like a standardization layer that ensures all of your tools and models can communicate consistently across the frameworks, and it's what allows you to plug the same tool into LangGraph and AutoGen without rewriting, the glue code. So that is the connector of everything here. Going to the demo. Okay. Let me quickly also show you the demo for this example. Right. So we have to install some dependencies, and we are going to have, LangGraph and LangChain. LangChain is the foundation, provides all the basic building blocks. And there's also LangChain OpenAI that are basically connectors to OpenAI's models like ChatGPT. The rest of the tools are easy, like you definitely need Python. There is the installation of SQLite, which is for state saving and basically checkpointing case. In real world, like after installing this, you want to get connected to an LLM, and in real world you would want an LLM to back your implementation. You have to, for some of them you have to pay. If not, you have to figure out like what model you want to use and how you can find free API keys. But this notebook is built such that it has like a failed safe mode, and you don't necessarily need the API key. We just want to show the different steps of the agent. That is why we do have a simple database built in this case. And just so we have the data, we do call database creation if we had an LLM agent, but if not, that is fine. And this is kind of like defensive programming. We need like network resiliency. What if the, Pi baseball API is down? What if there's no internet? Then your demo would work fine. And also speed, like how much time does it take to create this database. This is the core functionality that we are looking into. And there is a callback for, safety run Python. And basically we have, let me show you, we have the calling the LLM through its APIs that is provided. As beginning I said, we need the chat open API, and then we need the system message and the human message. System is the AI's personality and role. For example, we'll say you are a Python expert who writes safe and efficient code, and then there is the user that says, write a code for 2010 home run leader, something like this. And if, for example, we don't have a key, then this will fall into the safe run Python that generates the code for you. I created 2 samples of it so that the code is safe. So the code structure basically tries to use PyBaseball API. If it fails, then just goes the backup our CSV file, and I also call it in here. This one is for the LLM case, and this one is in case we don't have the LLM. I did add a lot of, like, at some point I used different models, and the code actually had errors in it, so I did add a lot of cases where to create the code safe. Like, it generated a Python file but it wasn't executable, so that is a lot of problems that I tried to solve the code. Sometimes, if you use open source LLMs, this is one thing that you would want to consider, is that you would want to make sure that the code that is generated is actually safe, right? It's not malicious or anything. These are the packages that I installed for checkpointing. LangGraph checkpoints SQLite is installed. You just need to make sure to include this in your packages. This is what we are actually looking at and what we are trying to learn. So we do have a class of orchestrator state. You can think of state as a shared notebook that gets passed around between different agents. Each agent reads from it, does the work, and then writes back to the node. And then it has like question what the user asked or plan the steps we'll take, and also the code, the Python code that is generated, the final result answer, or if there are any problems that are happening, and a log of what happened for the sake of debugging this case. And then we do have the executor graph, the executor state class, and this is the gen code, which is the executor node that we have. The gen code function is our code generation agent. It reads, you can see it reads from the state, and then it does the work. It says you generate minimal safe Python code, and then it writes, it writes the code to the state, and it returns, the modified state for us. So this is your executor node code. And then remember, like, that you need to craft the prompt really carefully. Then you have the run code, defines, executes the generated code. This is basically you create a Python code and then now you want to execute it. It has, the 2 paths. It has like a success path and failure path. Like, if it returns return code 0, then good, stores output, clears any previous errors. But there is also a failure path to it as well. And why do we store both of these? Sometimes, we generate a code and it fails, but produces useful partial output. We would want to save anything for debugging later. Now you can see the executor graph. These are the different nodes and how they communicate with each other. We first start, then we go to generate code, then we run code, and then after that we will end. Depending on whether we have failed or not, we can run code again or we can skip. And after all of this, we will be end, and then we compile our graph here. So then we have, the orchestrator nodes here, and the orchestrator node is like a planner, is like a project manager, And for example, we'll say identify the, then load some state, then compute the HR leader, then return the answer for us. So the orchestrator node is basically connecting everything together. We have, the planner that is planning the task, the delegate to executor, and then summarization. Delegate to executor is like, imagine like now all of these is like a magic of like multi-agent system, and we are calling the entire executor graph as if it's a single function. The orchestrator doesn't know or it doesn't care about the internal details of the code generation and execution. It's just going to execute this stuff. And then the summarizing handles the final formatting, like if there's an error, if it creates a user-friendly message, for example, for the executor, and you can see the orchestrator graph being built. Here is for the checkpointing of the graph, and we will basically create connection to SQLite database and attach it to the graph. Every time state changes, LangGraph automatically saves it to the database for us. And you can see, the output says checkpoint enable in this case. And there is also, this one, I will execute it. We can execute it so you can see the database here. Now we are, getting to the interesting part. There is like a user query that is the input and initiate the state dictionary. That's what we feed to the graph. We have a thread ID as well. It's a unique identifier for the conversation thread. And why do we need a thread ID? Is because of the checkpointing, tracks all the individual conversations. You can have multiple users asking different questions, each with their own thread ID, and so they won't interfere with each other. And you can see the string code in this case, that is for the sake of logging, saying which state we are in each time. And for example, every time we keep updating and then we move to the next node. So the initial state is our question, then we update, and then we go to the next step in this case. And you can see, after, running this cell, who let the MLB, because the database that we had was for baseball and the code that we are generating is for baseball. You can see the output. We are in the plan phase, then we are in the execute phase, and then we are in the summarize, and the answer actually comes from the database that we have generated in this use case. So yeah, that is just a quick demo of how the agents are being used. You can actually try to break the code as well. I did try to give it some like question about, asking whether, and you can actually, I believe in this one, it shows the error and it says like the Python code that you have generated doesn't work. But because we took care of all of the errors in the output handling, it moves on to the next steps. It doesn't just fail in this case. Yeah, so that is our final demo. Right, we didn't need a lot of stuff. We just need, for example, LangGraph or LangChain or any framework that you see fit for your use case. And we basically just Python package, maybe some OpenAI kit, something like this. And right, with a Jupyter notebook, you should be fine. And finally, I do want to talk about a little bit about, the key takeaways and, right, the key takeaways and the do's and don'ts about the agents, right? How, building block really matters. What is a tool? What is the role of memory? What is the role of, planning? And that patterns enable, complexity. We need to be production ready. Right. The agent's best practices, you should start with clear task definitions and success criteria. It seems very simple, but it is very critical. You should instrument everything. You need to think about tracing, logging, and evaluation hooks. Every tool call, every reasoning step, every token usage should be traceable. You should set explicit stop conditions. You shouldn't allow it to think forever. You need to validate all tool inputs and outputs, create the checkpoints, check that the data makes sense. And no system is perfect, so you may embrace, the human in the loop and, do integrations and check the checkpoints, integrate human checkpoints intentionally. And there are some don'ts. Don't overcomplicate simple tasks. Do we need a simple prompt or do we need a RAG? Don't skip the persistence. Like agents that forget like everything between runs are like, are useless. We need checkpointing, we need memory. You don't forget about the error handling. You can see any unexpected API call could just break your system. So you need to have like error handling as part of the automation. And finally, security controls, logs, rate limits, sanitize everything. And right, finally, that the building blocks really matter. Executive function, deciding what to do and in what order, memory for context engine, state and checkpointing gives you reliability. That's kind of like your save game system. Observability gives visibility, logs, traces, and metrics.